So we talked about how to find volumes of three-dimensional solids, and the trick was to find the cross-sectional area as a function of x or y, depending on how you're integrating, to find that volume. Well, that process can be simplified somewhat if we talk about solids of what we call a revolution. These are solids that are obtained by rotating a region in the plane about an axis or about a line in general, really. So cones and spheres are familiar examples of such solids. So for example, if I talk about this region right here in the first quadrant, x-axis, y-axis, this little triangular region, if I talk about rotating it about, say, the y-axis, I'll indicate that by sort of doing a little spin around. What do I mean by that? So it's going to be three-dimensional. This is in the plane here, but this region is going to sweep out and go all the way around, go back into the page, and then come around, and we are going to form a cone, right? When it goes back into the page, it will go here, and of course it's going to sweep out a circular pattern, right, as we swing that triangle all the way around. And we have a cone, right? We have a cone. A sphere can be formed by taking the top half of a circle. So let's take this region here and let's rotate it, say, about the x-axis, right? Then what shape are we going to get? We're going to get a sphere, right? It's going to come out towards us, all right? Hidden line back there. I don't know if you've ever seen those party decorations before or not, but they're little globes with like paper globes, but when you buy them, they're shaped like just a semicircle, and as you open it up and swing it out that shape, it forms into a sphere. That's sort of the idea of what we're talking about here. So if we can talk about this in general, what would it look like? So in general, if we have some continuous function f, and I'm going to have it be continuous and positive over the interval from a to b. So here is the graph of my function f, and let's consider the region under the graph of this function. I won't shade it in, but everything under the graph and above the x-axis here. So this is the x-axis here, we'll say. And we're going to rotate this region about the x-axis. So we're going to rotate it about the x-axis. That's how I indicate rotation. So this whole region is coming out towards us, right? Rotating around and going back into the page, and then rotating underneath and coming back out again. So when it goes back into the page down here, what's it going to look like? Well, I'm going to try and mirror that here as best I can. And probably a little closer there. Okay, so it's going to when this piece comes back and goes back in, right, it's going to look like that. And what are we going to have? We're going to have these circles. Hidden line here. And what do we have? It's like it's a vase that you can put flowers in or something, or a flask that you can put some kind of chemical liquid in or something. I don't know, something you might find in a lab. Okay, looking at it this way anyway. But or maybe it's some kind of goblet or glass looking this way. I don't know. But it's this region. And so how can we find the volume of this region? Well, again, from A to B, if we divide that up into n equally likely n equally equal with subintervals. I'm thinking of probability here. Equal with subintervals, and one arbitrary subinterval may be here to here, the ith subinterval, we'll say. Right, then I can approximate the area under this curve, first of all, with a rectangle And what's the height of that rectangle? Well, I can choose an arbitrary, I can choose the left endpoint, right endpoint, midpoint, any arbitrary point on this interval to obtain the height. Let's say I pick this value here, get the height of this. That gives me my rectangle, right? So we've done this before to estimate the area under the curve. So let's think about that rectangle right here. Now, when I rotate this rectangle, about the x-axis, what's going to happen? This rectangle is going to come out and then go back into the page and then come around and come back again and keep spinning it around, right? We're going to form this solid or approximation for the solid with these rectangles. And what shape are we going to get when we sweep out that shape with the rectangle? It's going to go back into the page here, right? And if I take a look at that, what's it going to look like? Well, it's going to be a circular, we call it disc. Okay, circular disc with a little thickness here, right? And what's that thickness from? That's the thickness of this rectangle, which we typically call what? Delta x, right? I mean, this is our so-called delta x width. That's going to be the thickness of that piece there. And then this, so what is the volume of this disk? Well, it's a circle, and so the area of the cross section is just pi times the radius squared, right? I'm going to use capital R for the radius here, so the area is pi times the radius squared. That's the area, and we want the area here to be as a function of x, because as x varies from A to B, we're looking at these different cross-sectional areas. And so, well, how can I find that cross-sectional area? Well, what is R? Well, R, if we think about it, notice from this is the x-axis coming out here, right, that we're rotating about. And so from the x-axis to the top of the rectangle, right, that right there, that's what R is. That's the value of R here. So the height of this rectangle is R. And what is R? It's just the value of the function, right? Notice that R is just f of x in this case, right? Just the height of that function. And so what we have then is that our volume, if you remember, integrating along the x-axis from A to B, and we just integrate this cross-sectional area, which is pi r squared, or pi what? F of x, quantity squared. Okay, and this is what we call then, because we get thin circular discs out of this method, we call it the disk method. The disk method. And so in general, if we are talking about r of x being the radius of that approximating disk, then, and if we have a horizontal axis of revolution, right, which means we're rotating about, something like we did with this semicircle to get the sphere, we rotated about the x-axis, and of course this shape we rotate about the x-axis, or any other horizontal line. It may not just be the x-axis, could be at y equal 1 or y equal 2 or something else. We'll see some modifications we can make, but any horizontal axis of revolution, then this is what we get here, okay, which is what we just derived. So for numbers 1 through 3, we're going to find the volume of the solid revolution formed by rotating the region in the first quadrant bounded by the given curves about the specified line. There are a lot of prepositional phrases in there, isn't there? So we got of, and we got in, and we got by, and we got about. Okay, so let's make sure we understand. First of all, let's look at the region that we're talking about for this first example. Y is equal to x squared. I've graphed that function for you already. And let's just label that as such. As y equal x squared. And then we have y equals 0, right? What is y equals 0? Well, that's the x-axis, isn't it? Right, when y is 0, we're talking about the x-axis. Okay, so that's the same as the x-axis. And then x equal 1, that's a vertical line, right? X equal 1. We'll do a different color for that. Right, so that's x equal 1. And do we see the region we're talking about? Do we see the region that we're talking about bounded by these three curves? Well, yeah, it's this little near triangular region. It's not a triangle because of this curve, right? It's not a line segment. And what are we going to do? We're going to rotate this about the x-axis. So we're going to rotate it about y equals 0, the x-axis. Okay. And what's going to happen is this piece is going to come down, and we're going to, right, it's going to go into the paper again, you know, here. So it's going to come around, go into the paper, and come down. I've tried to show what this thing looks like here with sort of a 3D modeling software that I have, and you could see that it sort of flares out, right? It's got a circular bottom here, circular, looking at it this way from the positive x-axis, right? It would have that circular, and then on looking at it this way, there's a real sharp point right there. This, right? You don't want to touch that. It's like a tack, right? You'll draw some blood or something. So when we do this, though, how do we set this up again? So remember, we're going to do an arbitrary interval here where we'll have this rectangle, all right? And we're going to rotate this rectangle about the x-axis along about y equals 0. And of course, what do we get? We get a circle, right, for our cross. So looking at this way, this would rotate around. We get a circle, and again, our radius is r. And that circle, right, its center is what? Is the y-axis, sorry, x-axis when y equals 0. The x-axis. And so what is the area of this region as a function of x? Well, it's just pi times the radius squared, right? Well, what is the radius? Well, the radius, again, goes from the x-axis to where? Really the top of this rectangle, right? So this right here, that right here is the value of r. And what is that equal to? That's just equal to this height is equal to what? X squared, because it's on the curve y equals x squared. The bottom is on the x-axis, right? So this height is exactly equal to x squared. And if I square x squared, I get x to the 4th. So there's my cross-sectional area as a function of x. And you can see that makes sense. You know, the radiuses of these circles, right? As I get closer to the y-axis, they get smaller and smaller, right? Smaller and smaller circles. In fact, right at x equals 0, we would expect the radius to diminish to 0. And it is true, if you plug in 0 into this formula, you get 0 for the area. On the other hand, right, the radius increases all the way up to 1, right? At x equal 1, you get 1 squared, which is 1. That's the radius at that point of the circle at the very end there. So now we're ready to find the volume. Where are we integrating from along the x-axis? Well, it's where this region is, right? This region, we're going to integrate from 0 to 1. I don't want to go anywhere but there. From 0 to 1, that's where that region is. That's what you have. It's real important to still draw this region so you know what region you're talking about. So I can get my limits of integration, and I just integrate this cross-sectional area. And then my dx just indicating it's with respect to x. So this one's pretty easy, right? The pi is a constant multiple. It can come out. What's the antiderivative of x to the 4th? That's just x to the 5th divided by 5. I'm evaluating at 1. It's 1/5. At 0, it's 0. 1/5 minus 0 is 1/5. And so this is 1/5 times pi, or pi fifths. Pi being about 3.14, so this is, you know, a little more than 3/5 or 0.6, a little more than 0.6. That's the volume now, right, in cubic units. So this is the capacity inside this kind of, I don't know, funnel-shaped thing, right? It's an interesting funnel-shaped thing. Okay, so that's how the disk method works. Let's take a look at another example, but this time, instead of a horizontal axis of revolution, going about, in this case, the x-axis, we're going to look at a vertical axis of revolution. So basically it's very similar, right? The cross section that we're integrating again is going to be a circle of radius capital R, but now it's a function of y. So it's pi, that constant multiple can come out, pi times the radius squared. We need the radius now as a function of y when we're doing a vertical axis of revolution. So here is our second example. Y is 1 minus x squared. So that's this curve right here, that parabola. Y equals 0, again, we know is the x-axis, and x equals 0 is the y-axis. And so we see the region then here that is bounded by these three curves, right? This little region here. Now we're rotating about the y-axis this time, right? So this is the y-axis here, so we're rotating about the y-axis, and this piece will go into here. What will this thing look like when we're done with it? It should be sort of this dome-shaped structure, right? So here, right here, would be the y-axis coming up, and here would be our x-axis. Okay, so this shape sweeps out a volume, a solid, right? And we're interested in the volume, the capacity inside this structure. We've got this dome structure. If we look at it from the bottom, we just see a big circle down there, but we want to know what's the volume of what's inside. And so we could do that. Notice this time, instead of integrating with respect to x, we're integrating with respect to y. And when we pick an arbitrary interval, our rectangle is no longer vertical, but it is horizontal. And we take that rectangle and we rotate it about the y-axis, and what do we get? Same thing, we get that thin circular disc, right? Thin circular disc, and its radius we've called capital R, and the center of this is, again, this time the y-axis. X equals 0, right? That's the y-axis. And so what's this radius? The radius is from here to the top of that rectangle. Okay, so down here I have what? This is obviously x equals 0, and this is y equals 1 minus x squared, but we need it in terms of y, as we need x as a function of y, because I'm integrating with respect to the y-axis here. Okay, and so this is x equals 0. This is what? Y equals 1 minus x squared. So we need this as a function of y. In other words, what I'm going to do is I'm going to solve for x. And I can solve for x by adding x squared and subtracting y from both sides of the equation. Do you see that? Adding x squared and subtracting y. And then what do? I take the square root. Now, normally when I take the square root in an equation, I would take both the positive and the negative square roots, right? Because it could be plus or minus this. However, we're talking about being in the first quadrant. Therefore, both x and y are positive. So just remind us that we're in the first quadrant. Okay, and so it's a weird looking first in first quadrant. So there it is. So what is our radius here? Our radius is exactly this value, right, which is 1 minus the square root of y, the square root of 1 minus y, minus x equals 0. oops, square root of 1 minus y. So, and just check, does this make sense? When y is 0, when y is this value, right? Y is 0 to 1 is what we're varying. When y is 0, our rectangle is all the way here, and that radius, right, is 1 unit, right? That circle is going to have a radius of 1. Is that true when y is 0? 1 minus 0 is 0. Square root of 1 is 1. And so, yes, that works. And then as y gets closer and closer to 1, what's happening to the radius? It's getting smaller and smaller. The circles are getting smaller and smaller. Radius is approaching 0. In fact, right at y equal 1, the radius should be 0. Is that the case with our formula? Yes. So you could check and make sure that your formula is indeed reflective of what you've drawn here. And that's real important. So our area of this now as a function of y is pi times capital R squared, right? Again, it's just the circular disk, circular area. But if I square R, I get 1 minus y. And there it is. I'm now ready to find the volume by integrating. And again, I'm integrating along the y-axis, so going from 0 to 1. Pi times 1 minus y dy. So I can integrate this. This pi comes out. The antiderivative of 1 is y, and the antiderivative of y is it's 1/2 y squared. Of course, it's negative from there. And we're evaluating this at 1 and at 0. If I evaluate it at 1, I have 1 minus 1/2. Evaluate at 0, 0 minus 0 is 0. 1 minus 1/2 is 1/2. And I get 1/2 pi very easily. That's the volume. Again, remember, this is the volume of the solid that we get from this revolution, from some rotating, again, this entire region about the y-axis in this case. Okay. All right. So we're going to stop here. When we resume, we're going to take a look at something known as the washer method, which is related, obviously, to this disk method, and we'll see how exactly.